Good morning, everyone. I'm Yuan from Tianjin University. Today, I'm honored to share our research for a dual congestion control loop for small and large flow in data centers. This work is a joint collaboration between Tianjin University, Peking University, and Huaxiahaorui. The bandwidth in data center networks is growing at a high pace. As you can see from the figure, from 2007 to 2024, we have witnessed a significant surge with speeds reaching up to 400 gigabits per second and beyond. The high-speed growth in bandwidth has brought new features to DCN traffic. More and more flows are becoming smaller and can be finished in fewer RTTs. For instance, on a 100 gigabit per second link, small flows can finish in about 3 RTTs. However, the large flows require hundreds of RTTs to complete. This difference in flow sizes and communication times poses a big challenge to congestion control in DCN. The goal of congestion control is always clear: to offer low latency for small flows and ensure high throughput for large flows. To achieve this goal, over the past decade, many researchers have put forward a variety of schemes for data center networks, which can be specifically categorized into the two types: reactive congestion control, such as DCTCP, DCQCN, and the proactive congestion control, such as HOMA, EUROSYS. However, the existing solutions still have flaws. Next, we will conduct a detailed analysis. Reactive congestion control, also called RCC, use the sender as control entity and use ECN, RTT, and INT as congestion feedback signals. However, due to the shared buffer and the signals of small and large flows, RCC is easier to misjudge the source of congestion. Proactive congestion control, which is also called PCC, relies on the receiver, switch, or apparator as control entity and the credit as a feedback signal. Here we take HOMA as an example. At start, all flow bursts 1 BDP data into a network, which can lead to buffer blocks and even packet loss. In the scheduling phase, regardless of whether the flow is large or small, HOMA receiver will send the credit packet to sender for each arriving packet to request the transmission of next packet. Eventually, the sending rate of small flows dropped or even timeout happened. In conclusion, the interwide rate control leads to performance degradation. So here we ask a question: can we decouple the rate control of small flows from that of large ones? Our answer is fork, a dual control loop transport design. This paper shows the overall of the fork. It consists of a sender-driven small flow control loop and a receiver-driven large flow control loop. We mark both small and large flows with per-port ECN to indicate congestion and use priority queues to protect the transmission of small flows at the switches. First, let me introduce SCP. Once a flow starts, it doesn't know the proper sending rate because it has no information. If we use slow start, it will add an intolerable delay for small flows that only need a few RTT to complete. Slack dropping like EUROSYS and ADP is a good idea, but late drop unscheduled packets first. Most of them are from small flows. So the key insight of fork SCP is using the congestion information from other small flows. Since fork adopts packet spraying for load balancing like other schemes, so congestion only occurs at the last hop. Therefore, fork groups small flows according to their destination because they experience the same congestion bottleneck. Moreover, we use a joint congestion window to share among these flows. One is there are multiple small flows at the same time. We choose the flow with the shortest remaining bytes to achieve the best performance. So why destination-based flow grouping works? We can here's an example. Before the flow is grouped, when the acknowledgement of small flow return, the small flow has already finished because it is too small, and the new flow has no idea at the beginning. After the flow is greeted, the new flow can use the available bandwidth detected by the previous flow to get its initial sending rate. In addition, SCP uses multi-flow ACK clocking to adjust the size of aggregation congestion control. Traditional transport like DCTZP adjust the window until window size ACK received, which is too slow for small flows to adapt to the dynamic networks. On the opposite side, per ACK updates a quick response speed, but is susceptible to noise. To balance the response speed and stability, we use two consecutive ECN marks as congestion signal. Here is the fork 4-state ACK generation state machine. We can see 0, 0 and 1, 0 means that the last two or one received ACK are not marked with ECN, so the congestion window can increase. 0, 1 and 1, 1 means the last one or two received ACK are marked with ECN, so the window should decrease. Moreover, we use alpha represents the number of consecutive ECNs received. The larger the alpha, the more congested the network is. So the greater the window will reduce. Let me introduce LCP. The goal of LCP is protect small flows while using the remaining bandwidth of small flows. Therefore, when congestion occurs, the sending rate of large flows should be reduced first to give bandwidth to small flows. LCP uses congestion diagnosis and ECM migration to achieve this goal. First, let me introduce two concepts. GC, which is grantable credits, represents the credits a receiver can send to all the big flows it receives. And we define two congestion types, which is CAL and CS, which means congestion caused by large flows or small flows. When an ECN marked packet arrives at the receiver, the LCP determines the congestion type. If the packet is from small flows, but the GC is still more than one, which means some large flows are active. So at this time, we think the congestion is caused by large flows and migrates the ECN mark from small flows. After congestion diagnosis, LCP adopts an AIMD method to adjust the number of credits sent to the large flows based on the congestion types. We set the initial grantable credit to 1 BDP. If we contact the congestion type is not CL, GC will be increased additively. Otherwise, if the CL event is detected, GC will be decreased multiplicatively. Next is the evaluation. We have implemented a fork per tab based on DBDK for evaluation. In our testbed setup, we connected X servers to a 100 gigabit per second switch. For simulations, we use the NS3 platform with the span leaf design topology and 64 servers. For both testbed and simulation, we use 5 realistic production workloads to evaluate our scheme. For small flows, compared to HOMA, LLOS, and DCPM, fork reduced the average FCT of small flows by up to 14, 67, and 66%, and the tail FCT by up to 47, 68, and 90%. For large flows, fork only delivers up to 14% gap for large flow average FCT, and compared to LOS and DCPM, fork even decreased the large FCT by up to 49 and 45%. Moreover, fork shows low threshold sensibility to different threshold settings. Fork can continue to deliver the lowest average FCT of small flows among all the conversions as long as the threshold is below 4 BDP. Another solution to decouple small and large flow may be static buffer allocation on the switch. However, data DCN traffic is a highly dynamic static allocation to catch the traffic variation. Second, small and large flows cannot complete each other succinctly. We compare HOMA static buffer allocation and fork at a different load with web server workload. The results shows that the static buffer allocation reduces small average by up to 12% compared to HOMA. But for fork can win-win for both small and large flows. In conclusion, fork successfully decouples the rate control of small and large flows through its dual control loop design. It offers ultra-low latency for small flows and effectively utilizes the spare bandwidth for large flows. With its host implementation, fork is highly deployable in real-world DCNs. Thank you all for your attention. That's all.
Questions?